Okay, welcome back. This is homework 16, and we're working on problem 2. So we have this hydraulic cylinder that's driving this link, which is in turn connected to this link LBC here, and this thing is moving at 4 feet per second to the left, and it's increasing at 3 feet per second squared. The dimensions are 1.5 feet here and 0.7 feet here. This is at 60 degrees, and this is at 60 degrees. So I've written out the problem. Let's get to it. Some of the first things that I want to do, we kind of work a little backwards here. We can see what the orientation of this piece is going to be. So it's going to have a line of action that draws something along these lines right here, whereas this is going to have a velocity coming this direction. So it's going to be let's go to the ICR then of this first link right in here. So I kind of drew him close to being at 60 degrees, but let's see. Something like that, maybe. Okay. So this is straight up. Oops, this is straight up. And if we take a look at here, here's the approximate line right in there. And something we might notice quickly is that we have 30 degrees right here, and this right here is then 60 degrees. We also note that this is 60 degrees, so that's 120 and 30, so this has to be 30 degrees. And we can, even though we didn't draw it perfectly, we know that this length is going to be the same as that length because these angles are opposite from each other. So the velocity right here, this is VA, it's going in this direction. So that's the ICR up here. So the angular velocity of this is omega AB. It's coming in this direction. So therefore, this thing is going to have a velocity, let's see, kind of make it something like that right there. So there's the velocity of C right in here. And put the RA with respect to ICR. And this is the, oh, I said VC, it should be VB. This should be RB with respect to ICR. And this distance, LAB, is 1.5 feet. So I'll do the work over on this side. Say that R, I guess A with respect to ICR, that's really what I need. It's going to be divided by the sine of 120. Is that right? And then, so this is going to be 1.5 divided by the sine of 30. I work that out, and I get 2.598 feet. So therefore, because I know that VA is equal to omega AB times R A with respect to ICR, I find omega AB is equal to VA over R A with respect to ICR, or I guess I could go down to the next line. I guess I'll put it right there. 4 feet divided by 2.598 feet, 4 feet per second right here. I end up with omega AB is going to be 1.5 396. I decided to go 5 sig figs, radians per second. And by the way, that's clockwise. And we can also, from observation, excuse me, RB with respect to ICR is equal to 1.5 feet, and therefore the velocity of B is equal to 1.53, I should write it out, omega AB RB with respect to ICR is equal to 1.5936 times 1.5, which means that VB is 2.3094 feet per second. All right, so now we go to do a velocity, and we could do a velocity and acceleration analysis. All right, so this was ICR of link AB. Let's do the link BC. The reason why I chose this problem is sort of like an opposite problem from some of the other cranks that we've done. So we have to think slightly differently. All right, so we have the velocity. We know the velocity is coming down and to the right. And by the way, we know these angles right here. This is 30 degrees. And this is the VB right there. So from that, we could tell that this thing has omega BC is coming in that direction. So we say, oh, VBC is omega BC times LBC. So omega BC is equal to VB over LBC, or 2.3094 divided by 0.75. So omega BC, which is one of the things that we were setting out to get, is going to be 3.079 radians per second, and we note that that's going to be counterclockwise right here. Okay, so while we're here, might as well do the acceleration analysis portion of this, and we find that the acceleration of, let's see, this is B right here, right? And this is C. So this is going to be B with respect to C in the normal direction. We know that the acceleration of B with respect to C is going to be omega BC squared LBC, which is 3.079 squared times 0.75, and so we get as a value here, wrote it down somewhere, there you go, 7.111 feet per second squared. And I'm going to go ahead and go alpha BC. I'm going to guess the direction. And so I also have acceleration of B with respect to C in the tangential direction. And that's going to be alpha BC LBC, so alpha BC times 0.75. Now this is 30 degrees as well. Don't quite have enough room to write this out, so I'm going to start next page. But I'm going to put this into the X and Y direction. I'm going to take these two and put them in the X and the Y direction. I think it'll simplify it just a little tiny bit, right? So let's take a look at those as we come through this. And so this is page 4, and this is problem 2 continued. And so my acceleration of B in the X direction, and I'm going to put it as positive and negative, right? So here is something that's kind of like important, could get you really mixed up, is I don't want to draw it like the arrows here. I'm going to put it as positive, negative, and then when I go to apply it to the other piece, let me see if I was true, if that's true. I'm gonna draw it onto the thing as if it's positive, okay? As if the arrows will be positive, but when I go to put the values back in, I'll put whatever's right here on the page, right? Trying to keep track because it can be very confusing. So this is going to be negative. Let's go for the one we know first. So going to have a positive in the X direction of 7.111, and it's going to be the sine of 30 degrees. And then, but this one's going to be negative alpha BC 0.75 and the cosine of 30 degrees. It's just gonna okay, so this just ever so slightly simplifies things. 3.556 minus 0.6495 alpha BC. And then I'll do the same thing for the Y direction. And so that's going to be, okay, so that's a negative right here. It's going to be a negative 7.111. And now the cosine of 30. And then it's going to be also negative here. Negative alpha BC 0.75, and now we want to have the sine of 30 degrees. So I'm going to rewrite this thing out and decided to go a negative 6.158 and a negative 0.375 alpha BC. Remembering that alpha BC in this case is assuming that it was going in a positive direction. Now I'm going to go for the 3 diagrams of this link right here. So we go the acceleration analysis, of link AB using 3 diagrams. And I'll just try to do my best with these. And the last one kind of started up here, kind of went down that far. Sure. All right, so applying the things that we know. We were given, this is one that we're given, acceleration of A, right? And here, like I said, I'm going to write this in here as if it was completely positive, but I'm going to put in these values when I get to it. It's, I guess maybe, as long as you can keep track of it, I think is people, professors and textbooks, solution manuals will do sort of a variation on this right here, their own method of doing it. All right, so I don't like how much longer that one is there. I kind of get the right. Okay, so we're going to apply this known. It's the simplest thing. Put it right here at both of them. And since we did that, we'll pin it right here. And here's one that we know. We're going to know that there's an acceleration in the normal direction coming down this way. And then this one, we don't know the acceleration. Let's see. Here is our omega AB. We know it's that direction. But let's assume alpha AB. We'll assume or guess the direction and make it positive. So that's this way right here. And that's going to be, this is B with respect to A. Did I do that right? B with respect to A, yes. Tangential, which is alpha AB times 1.5, right? Because this one is 1.5. Over here, let's see, I'll get rid of this line that's not necessary. I also want to maybe draw, make a little sketch. I think these sketches really help things. So this one right here is 30 degrees. And this is 30 degrees. And I'm not sure to put it over to the right of this or the left of it. I think I will put it over here. Acceleration of B with respect to A in the normal direction. Right, is that guy right here. And I like to do this separately instead of doing it in the equation, although I have been known to do it into the equations. That's omega AB squared LAB. Let's see, it's going to get in the way of this right here. I'm making a mess. Wish I had more room. I planned it out a little bit better. I'll put it down here. Acceleration of B with respect to A in the normal direction is going to be omega AB squared LAB, or what we found out previously was 3, nope. Where do we find it? 1.5. Let's see, did I mess that thing up? Yeah, no, I got it right. 1.5396 squared and then 1.5. So he turns out to be 3.556 feet per second squared. And it's interesting because we had another thing where we saw that was 3.556. Oh yeah, of this little value. But that, I guess that's just a coincidence, maybe. I don't know. Maybe some of symmetry might be affected by that. All right, so let's write out the thing that we're trying to get. We're trying to get this right here. So we're writing out the equation. The acceleration of B is equal to the acceleration of A plus the acceleration of B with respect to A in the tangential plus the acceleration of B with respect to A, and I kind of got that in the way, times the normal, or the normal component. So what I can do here is I know in its entirety, let's see, where is it? No, I have to, I'll just go in the X and the Y direction. That's right. So just take the X direction. And in the X direction, it's right up here, we take this equation. 3.5556, don't know why we did that many sig figs, minus 0.6495 alpha BC. It's going to be equal to negative acceleration of A, which was given to us, right? And that should be 3, -3 in the x direction. It's going x, going left. All right, so we'll go to the tangential next, and that's going to be negative as well, because it's going to the left. Alpha AB times 1.5 times the cosine of 30. All right, and then also, last one, this is negative as well, and it's going to be a negative 3.556 and the sine of 30. See, did I do that? All right, cool. So I have two unknowns in here. Let me rewrite them out. And so I will put it in terms here. And this, interestingly, does come out to 2.0000, depending on how many sig figs that you dropped off along the way, but mine worked out pretty well. And now I'll go in the y direction, and I will write down again what I had up here. So I can almost fit it right in there. Yeah. So I write negative 6.158 minus 0.375 alpha BC is equal to, all right, so there's nothing going on right here. So that's 0 in the y direction. Come on, focus. There you go. And this one is a positive, right? So we get a positive alpha AB times 1.5, and that's the sine of 30. And then this is also, no, this is negative. So that's negative 3.556 and the cosine of 30. So we get an alpha BC. I put it in terms of alpha of BC again. I get a negative 8.209 minus 2.00 alpha AB. So this is like equation 1 and equation 2. We equate 1 and 2, and I am left with, I guess I wrote it out again. I was just in a mood. 12.831 plus 2 alpha AB is equal to negative 8.209 minus 2.000 alpha AB. We get alpha AB is equal to negative 5.620 radians per second squared. So we guessed wrong. All right, so AB is going in the clockwise direction, but we'll use this back into either 1 or 2. So I'll write back into 1, doesn't matter. You don't need to see me do the math of this. That's BC, and that comes out to positive. So that one was in the counterclockwise direction. So now we're going to say answers, because the question, as you recall, was omega ABC and alpha BC. So we, for omega BC, and let's make it a vector, 3.08 radians per second clockwise, counterclockwise. And I could do this with an arrow, or I could say counterclockwise. And alpha BC, 2.31 radians per second squared counterclockwise. And let's put a box around it. The end. Nice long problem.